Usually when we talk about structural engineering or systems architecture, there's this fundamental expectation of precision and trust, really.
Right. It's quantifiable.
Exactly. Like you build a suspension bridge, you calculate the load-bearing capacity of the steel cables, you test the tensile strength, and the math just works.
Because the steel either holds the weight or it doesn't.
Right. You trust the metrics because the metrics are anchored in, the immutable laws of physics. It's clean. It's comforting.
But that is definitely not what we are seeing in AI right now.
Not even close. When you step into the world of frontier artificial intelligence research and development today, looking at the fresh data from the Stanford AI Index 2026, it feels like the equipment we are using to test the steel is fundamentally warping. We expect our structural math to work, but right now, the yardstick itself is bending. We have, millions of GPUs humming across the globe, hyperscalers spending hundreds of billions of dollars, and yet the models they produce are somehow simultaneously capable of writing complex microservices and entirely incapable of telling you what time it is on an analog wall clock.
It is the absolute definition of diagnostic muddy waters. The data we are seeing right now, it reveals a field that is scaling so aggressively and so fast that the systems around it, the evaluations, the infrastructure, the hardware supply chains.
The benchmarks.
Exactly, the benchmarks. They're all buckling under the weight of the technology itself. We are basically measuring phenomena we don't fully understand with rulers that are just breaking in our hands.
Which is exactly why we are cutting straight to the reality of the situation today. For you, the senior engineer, the technical leader, or the system architect listening to this deep dive, you really don't need another marketing pitch.
No, you don't.
You don't need a vendor telling you their new model is approaching generalized human intelligence.
Right.
You need to know what is actually happening at the frontier of AI model architecture.
Right, the actual math.
The actual math. You need to know how this is tangibly impacting software engineering workflows today, and you need to understand why the current methods for measuring AI capability are just failing. So, okay, let's unpack this. Because the era of blindly scaling models, just by throwing more compute at the problem, is hitting a critical physical inflection point.
It really is. To understand what AI can actually do for your engineering team today, we have to look at the raw inputs first. We have to look at the architectural shifts driving R&D. Because, the traditional philosophy for the last few years has essentially been brute force.
Just feed it everything.
Right. More data, more parameters, more compute. But the 2026 data shows that this approach is producing incredibly complex side effects. I mean, the sheer scale of the hardware build-out is staggering, but it's creating severe bottlenecks.
The numbers on that brute force approach are difficult to even visualize. Like, global AI compute capacity has grown by 3.3 times per year since 2022.
Which is exponential.
It's absurd. We are currently sitting at approximately 17.1 million H100 equivalent GPUs deployed globally. And NVIDIA is dominating this space, accounting for over 60% of that total compute capacity.
Yeah, but it's not just the chips, right? It's the physical footprint of where those chips actually live.
The data centers.
Exactly. That footprint is highly, highly localized. The United States hosts 5,427 data centers, which is it's more than 10 times any other country.
Oh, wow.
But the fragility of the system is alarming. Almost all of that leading AI compute, those 17.1 million H100 equivalents, they all flow through a single chip foundry in Taiwan, TSMC.
So we have an explosive 3.3x year-over-year growth in capacity, but it's totally bottlenecked by incredibly fragile global infrastructure.
Right. If there is a disruption at TSMC, the entire global R&D pipeline just grinds to a halt.
Which naturally dictates who gets to play at the frontier. Because, if the cost of admission is securing tens of thousands of highly sought-after GPUs from a constrained supply chain, you're effectively pricing out everyone except the largest corporations on the planet.
You absolutely are.
And the data confirms this absolute industry dominance. Out of 102 notable AI models released in 2025, 93 came from industry. That is over 90%. By comparison, academia produced exactly 2.
Just two notable models from universities. The academic institutions that, traditionally pioneered machine learning research, they have been completely marginalized.
They just can't afford the compute.
They can't. They simply cannot afford it. And the cost isn't just financial. It is severely constrained by data and by physical environmental reality. We are currently facing what researchers call the peak data dilemma.
Okay, let's dive into that, because peak data, it sounds like a theoretical wall, but it's actually an immediate engineering crisis.
Oh, it's here now.
For years, The strategy was just to scrape the entire internet, like ingest every single available piece of human-generated text, from Wikipedia to Reddit to, I don't know, obscure programming forums. But the well is running dry. You literally run out of high-quality human text.
And when you exhaust that supply of high-quality data, you can't just keep scaling parameters and expect the model to get smarter.
Right.
In fact, feeding it low-quality, synthetic, or highly repetitive data actually degrades performance. It makes the model worse.
Huh.
This is exactly why we are seeing a massive architectural shift toward what the industry is calling data-centric methods. The focus has entirely moved from the size of the neural network to the surgical curation of the training data.
Which brings us to one of the most surprising comparisons in the entire report.
Huh.
I love this part. Look at Grok 4. It's an absolute behemoth. 3 trillion parameters. It requires massive clusters to even perform basic inference. Now compare that to a model called OMO 3.1 Think 32B.
Right, the Allen Institute model.
Yeah. And as the name implies, it contains roughly 32 billion parameters.
Yeah.
That means OMO has nearly 90 times fewer parameters than Grok 4.
90 times.
90 times smaller. And yet, OMO 3.1 Think 32B achieves comparable performance on advanced, highly complex benchmarks, like the ANI 2025, which tests advanced mathematical reasoning.
It is a stunning validation of data-centric architecture. You have a model 90 times smaller punching in the exact same weight class as a 3 trillion parameter giant.
How does that actually work mechanically?
Yeah.
I think we need to break down what data pruning really means for the engineer listening right now. Because, it sounds like we used to just drill for crude oil everywhere, and we didn't care how messy it was because the oil was practically bubbling up out of the ground.
Right, just scoop it up.
Yeah, but now that the easy surface-level oil is gone, labs are being forced to build these hyper-advanced refineries to basically squeeze every last drop of energy out of a single drop of data.
The refinery analogy works perfectly for the extraction process, but we need to take it a step further to understand the mechanics of what's happening. When we talk about data curation, we are fundamentally altering the chemistry of the intelligence we get out.
Okay, how so?
Well, the researchers behind Almo 3.1, they didn't just dump raw web data into a training run. They utilized aggressive data pruning and exhaustive deduplication. Mathematically, what they're doing is projecting the training data into an embedding space and clustering it.
Okay, so mapping it out.
Right. They look for dense clusters of repeated information, say, I don't know, 50,000 identical forks of a GitHub repository, or millions of SEO-optimized articles saying the exact same thing about how to boil an egg.
So they are mapping the redundancy.
Exactly. When a model trains on highly redundant data, its parameters become saturated trying to memorize the specific statistical frequencies of that repetition, rather than actually learning the underlying logical concepts.
Oh, wow.
Yeah. So by aggressively pruning those dense clusters and leaving only the sparse, high information density vectors, you force the model's parameters to learn generalizable rules instead of just memorizing boilerplate text.
I see. So by throwing away, say, 80% of the data, the 20% that remains actually utilizes the model's weights more efficiently. You are forcing the network to generalize because it can't rely on rote memorization anymore.
Exactly. And they combine this with stage-specific training curricula. You don't teach a human calculus at the exact same time you teach them basic addition.
Right.
Almo 3.1 organizes the data into a curriculum. It feeds foundational syntax and grammar first, and then it progressively introduces higher-order logic and complex code repositories much later in the training run. This architectural shift proves that quality strictly beats quantity.
It's not just a theory anymore.
No, and frankly, this is no longer just a preference for researchers. It is a hard physical engineering imperative.
Because the physical cost of the brute force method is becoming catastrophic. Let's look at the environmental metrics for a second. Grok 4's estimated training emissions reached 72,816 tons of CO2 equivalent.
That number is just, it's hard to fathom.
It is. That is more than the lifetime carbon emissions of roughly 1,000 average passenger cars, entirely consumed for a single training run.
And the power capacity requirements are even more alarming. The aggregated power demand for these frontier AI data centers has risen to 29.6 gigawatts.
29.6 gigawatts.
Right. To put that in perspective, 29.6 gigawatts is comparable to the peak energy demand of the entire state of New York.
That's insane.
You cannot sustain that indefinitely. You literally cannot physically build enough nuclear reactors or secure enough grid capacity to support an industry that doubles its gigawatt requirement every 18 months.
Right. And if the cost of admission as a 29-gigawatt power plant and a multi-billion-dollar cluster of GPUs, it really begs the question of who's actually left in the arena.
Very few.
And this intense concentration of capital and infrastructure,
Mm.
it directly leads to a massive transparency problem. The secrets of how to build these hyper-efficient data refineries, like the deduplication algorithms, the curation techniques, the exact staging of those training curricula you mentioned, they're being aggressively locked away.
They really are. In 2025, 81 of the 102 notable models were released without their training code. The dataset sizes, the parameter counts, the specific hyperparameters used during the training runs, all of this is increasingly withheld by the frontier labs.
So it's a total black box.
Complete black box. We are moving rapidly from a culture of open scientific publication to a culture of strict corporate secrecy.
Which is a fundamental hazard for you as an engineering leader trying to integrate these tools into your stack. I mean, if you're building enterprise software, you need to understand your dependencies.
Absolutely.
If your core reasoning engine is a black box, you cannot audit it. You cannot predict its edge cases effectively. You don't know what data it ingested, which means you don't know its inherent biases or its vulnerabilities. You are entirely at the mercy of the vendor's marketing claims.
Now, the labs, of course, they argue that withholding this information is necessary for safety, right? Preventing malicious actors from replicating frontier capabilities. But the practical reality for the software engineer is that you are deploying non-deterministic, opaque systems into production environments.
And this severe lockdown naturally forces us to ask a big question. If the well-funded labs are hiding all their architectural secrets, what is happening to the open source community?
It's a great question.
Is open source R&D effectively dead, just crushed under the weight of $150 billion capital expenditures, or is it finding a different path?
It is absolutely finding a different path, and the dynamics are shifting in ways that directly challenge the hyperscalers' entire business models. Let's look at the performance gap between open-weight and closed-weight models. In 2024, that gap had shrunk to almost nothing. In 2025, it reopened, but really only slightly.
Yeah, the data shows that as of March 2026, the top closed-weight model is Claude Opus 4.6, and that's sitting at an ELO rating of 1,503. The top open-weight model is GLM-5, sitting at 1,454 ELO. So Claude Opus 4.6 leads by exactly 3.4% or 49 points.
Right.
And that margin is up from a razor-thin 0.5% gap back in August 2024. So, yes, closed source did pull ahead again.
They pulled ahead, but a 3.4% advantage is remarkably small when you consider the vast disparity in funding and compute between those proprietary labs and the open source ecosystem.
It's tiny.
And while that specific gap widens slightly, the broader geopolitical R&D gap has essentially evaporated.
The U.S. versus China dynamic here is fascinating. The U.S. is still producing a higher volume of top-tier models. Like in 2025, the U.S. produced 59 notable models compared to China's 35. But the actual capability gap between the best models from each country is practically non-existent.
Look at the timeline for a second. In February 2025, China's DeepSeek R1 trailed the absolute best U.S. model by just 0.4%. That's a mere 5 ELO points.
Right.
By March 2026, the U.S. lead was merely 2.7%, or 39 points. The U.S. and China have basically been trading the #1 spot back and forth for over a year.
How is that even possible? I mean, the U.S. has the dominant share of H100s, the U.S. has the lion's share of the CAB-X, and export controls were specifically designed to prevent Chinese labs from acquiring the necessary compute to train frontier models. If they don't have the brute force hardware, how are they keeping the gap under 3%?
Because they stopped trying to win the compute war. They focused entirely on architectural efficiency. They innovated around the bottleneck. A prime example of this is how models like DeepSeek R1 utilize reinforcement learning innovations, specifically an approach called GRPO, or Group Relative Policy Optimization.
Okay, let's break down GRPO, because this is a massive technical shift. Traditional reinforcement learning, like RLHF, usually requires a separate, massive critic model to evaluate and score the outputs of the primary model during training, right?
Exactly. In traditional setups, you have your main model generating answers and a second, equally large reward model grading those answers.
So double work.
Double the memory, double the compute, and massive amounts of human-labeled data to train the reward model in the first place. It is incredibly expensive and slow.
So how does GRPO bypass that? What's the trick?
The GRPO completely eliminates the need for that massive secondary critic model. Instead of having a separate neural network grade the output, the main model generates a group of different possible answers to a single prompt.
Okay.
Then the system uses a predefined rule-based checker to score them. For example, if it's a math problem, the rule checker simply looks at the final formatted answer to see if it matches the known correct integer. Or if it's code, it just runs the code against a set of unit tests.
So it's deterministic scoring.
It's deterministic scoring. The system then compares the scores of all the generated answers within that specific group and updates the model's policy based on which outputs in that group performed better relative to the other.
Oh, that makes so much sense.
By comparing groups of generated outputs against predefined rules, they drastically reduce training complexity and memory overhead. They can train highly advanced reasoning capabilities using a fraction of the compute required by traditional RLHF methods.
It's a brilliant workaround. They couldn't get the hardware, so they rewrote the algorithm to make the hardware they had exponentially more efficient.
Necessity is the mother of invention.
Truly. And this kind of architectural innovation isn't just happening in isolated international labs. The broader open source community is adopting these techniques and scaling massively. The Stanford report highlights 5.6 million AI projects on GitHub in 2025,
That's a huge number.
which is up 23.7% year over year. Model uploads on Hugging Face have tripled since 2023.
You have an incredibly vibrant, decentralized ecosystem of developers sharing model weights, publishing fine-tuning techniques, and building incrementally on top of each other's breakthroughs. It creates this compounding effect that allows the open source community to rapidly close the gap whenever proprietary labs make a leap forward.
And here is where it gets incredibly relevant for your business strategy as a listener.
Yeah.
If the performance gap between the absolute top-tier proprietary models, the ones that cost billions to train, and the open source or internationally developed models is only 3.4% or 2.7%.
Right.
As a senior engineer or a CTO, that is effectively a rounding error in practical day-to-day deployment. If I'm building a customer service chatbot or an internal log analysis tool, I do not notice a 3% difference in reasoning capability.
You don't. You really don't. For 99% of enterprise use cases, a model that is 3% less capable than the bleeding edge is still vastly overqualified for the task at hand.
So why on earth are hyperscalers spending $150 billion in capital expenditure? Why pour the GDP of a small nation into a 29-gigawatt data center just to beat the open source alternative by 3%? It seems financially irrational.
For the hyperscalers at the absolute frontier, they are fighting tooth and nail for those marginal gains because they operate under the thesis that a 3% difference at the bleeding edge might eventually unlock fundamentally new capabilities.
The AGI dream.
Right. They are hunting for phase transitions. True, generalized autonomous reasoning. To them, that 3% might be the difference between a model that requires constant human supervision and an autonomous agent that can independently execute week-long corporate workflows. They are betting that whoever crosses that autonomous threshold first takes the entire market.
Winner takes all. But until that theoretical phase transition happens, what does this mean for the tech industry today?
What we're witnessing right now is the democratization of the baseline.
The democratization of the baseline. That fundamentally rewrites the sauce playbook.
It absolutely does. It means that highly capable near-frontier intelligence is now effectively a commodity. You don't need a billion-dollar R&D budget to access intelligence that would have been considered state-of-the-art just 18 months ago.
Right, you can just download it.
You can pull an open-weight model off Hugging Face, fine-tune it on your proprietary enterprise data using a handful of rented GPUs, and deploy a highly specialized, locally hosted system that rivals the big APIs.
And because that capability gap has shrunk to a commodity level, the competitive pressure on the market is drastically shifting. Vendors can no longer build a moat just by claiming they have the smartest model.
No, raw intelligence is table stakes now.
Exactly. They now have to compete on operational metrics. Cost per million tokens, inference latency, API reliability, and enterprise data privacy guarantees.
If you are an engineering leader evaluating vendors, your procurement strategy should reflect this. You shouldn't be paying massive premiums for marginal gains in raw capability unless your specific use case demands the absolute frontier of complex reasoning.
Which brings us perfectly to the next major phase of this deep dive. If raw intelligence is becoming a commodity and highly capable models are everywhere, the true test for these tools isn't how they score on abstract reasoning benchmarks.
Right.
The true test is how they perform on actual day-to-day software engineering tasks. We need to talk about snippet generation versus autonomous systems engineering. How much of your team's job or your own job is actually about to be automated?
To answer that accurately, we have to move away from the generalized trivia test and look at the evaluations that test real coding ability in complex environments. And the data from 2026 presents a very stark tale of two extremes.
Okay, let's start with the extreme success. There is a benchmark called SWE Bench Verified.
Right.
This is a rigorous test of a model's ability to resolve real, human-validated GitHub issues within an existing complex codebase. We aren't talking about writing a simple Python script from scratch. We are talking about dropping a model into an unfamiliar repository and asking it to fix a documented bug. And the progress here over the last year is genuinely explosive.
It is. Performance on SWE Bench Verified rose from about 60% in 2024 to near 100% of meeting the human baseline in a single year.
Wow.
Specifically, Claude 4.5 Opus hit 76.8% absolute accuracy. Other top models, like Kimi K2.5 and GPT 5.2, are tightly clustered right behind it in the 70 to 76% range.
So they are absolutely crushing isolated bug fixes.
They are incredibly effective at localized, short-horizon reasoning. If you point a model at a specific bug in a specific file, provide the stack trace, and give it the surrounding context, it can generate the correct patch almost flawlessly. The models understand syntax, they understand local logic, and they can refactor existing functions with remarkable precision.
But the reality check comes when you ask the model to step back and do more than fix a localized issue.
The drop-off is severe, and it is measured by a benchmark called Vibe Code Bench.
Vibe Code Bench is fascinating because it doesn't just ask the model to fix a bug in existing code. It asks the model to build complete end-to-end web applications autonomously, entirely from scratch.
From zero.
From zero. We're talking about scaffolding the front end, setting up the back end routing, designing the database schema, and making sure the state management flows correctly across all layers. And here performance absolutely plummets.
It falls off a cliff. On Vibe Code Bench, the top model in the world, Claude Opus 4.6, leads at just 56.5% accuracy.
56.5.
Yes, GPT 5.2 follows at nearly 47%. And the vast majority of other frontier models fall completely off that cliff, dropping below 30% accuracy.
The spread there is wild. It's about a 46 percentage point difference between the top and the bottom models. Even the absolute best model in the world fails almost half the time when asked to build an app from scratch.
This beautifully illustrates the cognitive difference between AI as a bug fixer versus AI as an architect. Generating a snippet of code or modifying an existing function requires short-horizon reasoning. The constraints, the variables, the imports, they are already defined by the surrounding code.
Right, the guardrails are there.
Exactly. The model just has to connect point A to point B.
But standing up a project from zero requires extended, multi-step logical chains. The model has to plan the architecture, manage complex dependencies across multiple files, create the directory structure, and maintain the mental context of how the database schema it designed in Step 1 interacts with the API route it is writing in Step 15.
It is the difference between playing chess by only looking at the immediately adjacent squares versus seeing the entire board and planning 10 moves ahead. These models struggle immensely with maintaining coherent state over long horizons.
For the engineering manager listening, I think the most accurate way to conceptualize current AI is to think of it as a brilliant, hyper-focused junior developer. If you hand this AI junior dev a highly scoped JIRA ticket like, hey, the pagination on the user table component is broken, the offset logic is wrong, please fix it, they will crush it perfectly in 5 seconds.
And then we'll write the unit test for it.
Exactly. But if you walk up to that same AI junior developer and say, hey, please design and implement our new microservices architecture for the payment gateway, and you leave them completely unsupervised, they're going to absolutely crash the server.
Oh, 100%.
They will hallucinate a database library that doesn't exist, they will create circular dependencies, and they will implement a completely unscalable security model. They do not have the architectural context or the horizon planning to execute it.
And the research being done right now to bridge this exact gap is fascinating. The bottleneck isn't necessarily that the models are incapable of generating the right code for a payment gateway. The bottleneck is that they lack built-in reliable verification protocols.
Meaning what, exactly?
Meaning they cannot autonomously self-correct over long time horizons.
How does human self-correction differ from the model's approach?
Well, think about your own workflow. When a human engineer builds an app, they don't write 10,000 lines of code blindly and then hit run. They write a function, they test it, they see an error, they read the stack trace, they understand why the logic failed, and they adjust. They iterate based on verified external feedback.
We use the compiler and the runtime environment as a constant reality check.
Precisely. Current AI models struggle immensely with this iterative self-correction. If an autonomous agent makes a subtle logical error in step 2 of a 50-step scaffolding process, it often doesn't catch it. It lacks the internal mechanism to pause, verify, and realize the mistake.
So it just keeps going.
It just keeps building, so that error compounds. By step 15, it's building functions on top of a broken foundation, and the entire application inevitably breaks at step 49. Until the industry develops rigorous, programmatic self-correction loops and integrated verification environments for these models, autonomous system architecture remains out of reach.
And this limitation is creating a really thorny macroeconomic issue in the data. The report outlines what we can call the productivity paradox. The AI Index notes that studies are showing 14 to 26% productivity gains in software development. Developers are using Copilot, they're using Claude, and they're getting objectively faster at writing boilerplate and fixing routine bugs.
The micro-level efficiency is undeniably increasing.
But at the exact same time, U.S. employment for entry-level developers, specifically those aged 22 to 25, dropped by nearly 20% in 2024.
It is a stark structural reality. The productivity gains from AI are materializing in the exact same domains where entry-level employment is precipitously declining.
The economic math for a company becomes ruthless. If your senior engineers are suddenly 25% more productive because an AI is handling all their routine bug fixes, test generation, and boilerplate code, the immediate financial incentive for a CFO is to simply hire fewer junior developers.
Right.
You don't need a team of 5 junior devs to handle the backlog if your 2 senior engineers can clear it with AI assistance.
Which creates a critical long-term vulnerability for the entire software industry. We are solving a short-term efficiency problem by creating a massive pipeline problem.
Yeah.
How does an engineer acquire 10 years of complex architectural experience if the jobs that give them their first 2 years of foundational experience are automated away?
It's terrifying. The AI is replacing the localized task execution, but it fundamentally cannot replace the senior-level architectural judgment. The risk is that we are hollowing out the training ground for that exact judgment. In 10 years, who is going to architect the systems if no one was ever allowed to be a junior developer?
It is a structural labor challenge that the tech industry has not even begun to solve, and it leads us directly to the core technical tension of this entire report. We are talking about models hitting 76% on complex coding tasks like SW Bench. We have vendors plastering their websites with claims that their new models are beating human baselines across the board.
Yet any senior engineer listening to this knows from personal daily experience that there is a massive disconnect between those glossy benchmark scores and the messy reality of engineering.
Oh, a huge disconnect.
If you use these frontier tools for more than an hour, they will inevitably hallucinate an API endpoint that was deprecated 3 years ago, or they will confidently fail at a basic logical puzzle.
The daily experience of the developer completely contradicts the marketing metrics.
Which brings us to the most critical revelation in the Stanford AI Index 2026, the evaluation crisis. Our rulers are fundamentally broken.
We are suffering from an industry-wide phenomenon called benchmark saturation. The models are evolving so quickly and adjusting so much data that they are rendering our standardized tests obsolete in a matter of months.
Let's look at a benchmark called Humanity's Last Exam. I love the dramatic naming convention here, but it was specifically designed by researchers to be incredibly difficult. It is packed with PhD-level, highly obscure questions designed to stump AI and favor deeply specialized human experts. And yet, frontier models gained 30 percentage points on this exam in a single year.
A 30-point gain on a PhD-level exam in 12 months is unheard of. And when these tests saturate so quickly, they completely lose their statistical utility. They lose their ability to distinguish between models.
Right. Look at MMLU Pro. This is a massive, widely cited test of broad multitask knowledge. It was designed to prevent guessing by using complex 10-option, multiple-choice questions. As of early 2026, the top 15 models in the world are all squashed together at the very top of the leaderboard.
Just piled up.
Yeah, they all score above 87%. The total spread between the 15th place model and the first place model, which happens to be Gemini 3.1 Pro at 91.2%, is just over 4 percentage points.
If the top 15 competitors are all within 4% of each other, the test is no longer a useful discriminator. It's just a traffic jam at the finish line. It tells an engineering manager absolutely nothing about which model is actually better suited for their specific deployment.
But saturation isn't even the scariest part. The scariest part is the outright mathematical and logical errors embedded in the benchmarks themselves.
This is where the foundation really starts to crumble. A staggering review by Stanford researchers looked closely at the reliability of these widely used evaluations. They found invalid question rates of up to 42% on benchmarks like GSM-8K.
GSM-8K is the standard test for grade school math reasoning. Every major AI lab uses it to prove their model can do math.
And yet, 42% of the questions are structurally flawed. They contain incorrect answers in the key, ambiguous phrasing, or logical impossibilities.
42%. Think about that in the context of structural engineering. If a contractor builds a house using a tape measure that is literally missing half of its inches, you do not trust the house.
You'd run away.
Exactly. It doesn't matter how beautiful the blueprints are, the underlying math is corrupted. How can any technical leader trust the marketing claims of an AI vendor if the metrics used to sell the tool have a 42% error rate?
You can't. Relying on those metrics is engineering malpractice at this point, and that fundamental invalidity is severely compounded by the problem of data contamination.
Okay, let's explain contamination clearly, because this is the dirty open secret of AI R&D.
Contamination happens at the pre-training layer. When a frontier lab trains a model, as we discussed earlier, they are scraping vast swaths of the internet. GitHub repositories, academic forums, research papers. By doing so, they inevitably and sometimes accidentally ingest the exact questions and answers from the public benchmarks.
Because researchers publish the benchmarks online so people can use them.
Exactly. The benchmark datasets are sitting in public GitHub repos, so the web scraper pulls them into the training data. When the model takes the test months later, it is not actually reasoning through the problem from first principles. It has essentially memorized the answer key. It is taking an open book test disguised as a closed book exam.
It's like giving a student the final exam to study from and then being shocked when they score a 99%. It proves nothing about their generalized intelligence. It only proves they have a great memory. And developers are absolutely optimizing for this, whether they admit it or not. There is a massive debate right now about leaderboard gaming.
Look at platforms like the Arena leaderboard. This platform relies on crowdsourced human evaluation. Users prompt two anonymous models side by side and vote blindly on which output they prefer.
The vibe check.
It was supposed to be the ultimate vibe check on model capability, but currently the top 4 companies are clustered within just 25 ELO points of each other.
Is that true parity in underlying intelligence, or are these labs just fine-tuning their models to adopt the exact conversational style, the formatting, the obsequious tone that human voters on that specific platform happen to prefer?
The research strongly suggests it is the latter. The labs are heavily using RLHF reinforcement learning from human feedback to adapt to the specific preferences of the platform, rather than actually improving the model's core reasoning capability.
Oh, wow.
They train the models to use bullet points, to adopt a confident tone, to apologize profusely when challenged. They are optimizing for the illusion of intelligence.
And this leads to my absolute favorite concept in the entire Stanford report, the jagged frontier of AI intelligence. Because these models are optimized for specific benchmark formats, and because they are trained on massive, uneven distributions of web data, their capabilities are wildly disproportionate. They do not possess a smooth, continuous spectrum of intelligence like a human does.
No, a human's cognitive abilities are generally correlated. If you are brilliant at advanced calculus, you generally know how to tie your shoes and read a clock. AI does not work that way.
Right. The jagged frontier is like hiring an elite astrophysicist to run your server architecture, and then discovering they occasionally forget how to open a door.
That's a great way to put it.
Here is the ultimate example from the data. A model called Gemini DeepThink earned a gold medal at the 2025 International Mathematical Olympiad. It scored 35 points, working autonomously for 4.5 hours to solve mathematical proofs that are entirely incomprehensible to 99.9% of the human population.
It is a truly elite, superhuman level of abstract mathematical reasoning.
Yes, but on another benchmark called Clockbench, which is designed to test basic visual reasoning, the absolute best frontier models can only read an analog clock correctly 50.1% of the time.
Right.
A human reads an analog clock correctly 90.1% of the time.
So you have an artificial intelligence that is a literal gold medalist math Olympian capable of solving theoretical geometry. but it essentially has to flip a coin to tell you what time it is on the wall clock behind you.
That is the jagged frontier. It is the perfect encapsulation of how bizarre and alien these systems are.
It proves conclusively that these models do not possess generalized human-like intelligence. They possess isolated pockets of extreme superhuman capability, sitting immediately adjacent to pockets of inexplicable incompetence. The landscape of their intelligence is jagged.
And this raises the most important question for you, the engineer listening. How on earth do you evaluate AI moving forward? If the tape measures are broken, the answers are memorized, and the intelligence is this jagged. If you are an engineering manager, you can't look at a dashboard that says 91% on MMLU and have any confidence whatsoever that this tool will actually help your team deploy a Kubernetes cluster without breaking production.
You cannot trust generalized benchmarks anymore. The report suggests that the industry must pivot immediately toward what are called centaur evaluations.
Centaur evaluations, like the half-human, half-horse from mythology. Let's break down how that works in a practical engineering context.
The core philosophy of a centaur evaluation is that we need to stop testing AI models in complete isolation. In the real enterprise world, an AI doesn't sit in a sterile void answering multiple choice questions about Python syntax. It is deployed as a tool. It works alongside a human developer.
Right.
Therefore, centaur evaluations measure how well a human AI team performs together on a complex task compared to a human working alone.
That makes infinitely more sense for a business. It measures the actual delta in productivity and success. Does this AI assistant actually make my senior developer faster at standing up a database schema? Or does it generate so much subtly broken, hallucinated code that my developer spends twice as long debugging it than if they had just written it from scratch?
Precisely. Centaur evaluations measure interpretability, helpfulness, integration friction, and synergy. If a model generates brilliant code but presents it in a way that the human engineer cannot easily read, verify, or integrate, the model is failing in a real-world deployment. These are qualities that traditional, isolated benchmarks completely ignore, but they are the only metrics that actually matter for enterprise ROI.
This has been an incredibly dense, highly technical journey through the R&D landscape of the Stanford AI Index 2026. Let's synthesize exactly what we've covered today for the technical leaders who have to go back to their teams tomorrow and make architectural decisions.
We started by analyzing the raw physical inputs. The compute required to train these frontier models is scaling exponentially, growing 3.3x a year to 17.1 million GPUs, but the supply of human data is exhausted.
Peak data.
The era of brute force web scraping is over, giving way to highly surgical data pruning, deduplication, and stage-specific curricula. This architectural shift is allowing dramatically smaller models to punch far above their weight class, proving that data quality strictly beats parameter quantity.
But the massive financial and environmental cost of this infrastructure, pulling 29.6 gigawatts of power, is leading to a severe lockdown in transparency, with over 80% of models hiding their architectural secrets. Yet, despite that lockdown, the open source community and international labs are innovating around the compute bottlenecks using techniques like GRPO.
Which means the capability gap is closing rapidly. The US and China are essentially at parity, trading the lead by mere fractions of a percent. The performance gap between closed and open source models is hovering at just 3.4%.
Democratization of the baseline.
Yes, highly capable near-frontier intelligence is becoming commoditized, which fundamentally shifts the enterprise battleground from raw intelligence to operational cost, latency, and reliability.
And in the software engineering space, that reliability is being severely tested. We have models that are absolute masters of the snippet, crushing isolated bug fixes on SWE bench at near 100% human parity, but they are failing spectacularly at the architectural level, unable to autonomously build and verify entire systems over long time horizons on Vibe code bench.
And that specific dynamic, automating the simple while failing at the complex, is already reshaping the labor market, driving a 20% drop in entry-level developer roles and threatening the future training pipeline for senior architects.
And overarching all of this is the evaluation crisis. The metrics we use to judge this progress are buckling. The standard benchmarks are saturated, heavily contaminated by pre-training data, and in many cases mathematically invalid. We are navigating a jagged frontier of alien intelligence using a fundamentally broken tape measure.
It's a challenging environment to navigate.
Which leaves us with a final provocative thought for you to mull over as we wrap up this deep dive. As AI models hit the absolute ceiling of these static, standardized tests, the future of research and development isn't just about building smarter models. It is about engineering entirely new ways to measure intelligence.
The paradigm has to shift from testing the tool to testing the integration.
Exactly. So if you as an engineering leader are evaluating a new AI coding assistant for your stack tomorrow, do you trust the 90% benchmark scores plastered all over their glossy marketing website? Or do you need to stop looking at their generalized metrics entirely and instead invest the resources to build a custom Centaur evaluation tailored strictly to your own proprietary code base to see if the human AI team actually moves the needle for your business?
You cannot manage what you cannot accurately measure, and right now, the only measurement you can trust is the one you build yourself.
That is the ultimate takeaway. You wouldn't build a suspension bridge without verifying the math on your own stress tests, and you absolutely shouldn't deploy an AI architecture without doing the exact same thing. Thank you for joining us on this deep dive into the true frontier of AI R&D. Keep a skeptical, data-driven eye on the horizon, and we'll see you next time.